Hi everyone. Today we're going to look at a multi-stage experiments. So a lot of the time that we run experiments in probability, we're not too interested in just a single stage, but more multi-stages. So think of things like when you're playing Monopoly and you roll 2 dice instead of just the one. We're interested in things like the probabilities of rolling, let's say, a double, or in that case that you've already rolled 3 doubles, avoiding that third one. And so when it comes to multi-stage experiments, we do them in what we call stages, right? And so let's say we are rolling 2 dice. Well, we might consider that first dice to be roll 1 and that second die to be roll 2, even though we're rolling them at the same time. So we can show the sample space for a 2-stage experiment using a tree diagram or an array. But anything beyond 2 stages, I would highly suggest a tree diagram be used instead. So, for example, we have a fair coin being tossed twice. And so if we call this, let's say, trial 1, and we call this one trial 2, well, the 2 outcomes when I flip a coin are going to be heads and tails. And so let's say coin 1 was a heads and coin 2 was a heads as well. Well, then I've got heads, heads, tail, heads, heads, tails, and tails, tails. And so our probabilities here are going to be out of 4 because we've got the 4 outcomes. So the probability of one head being observed, and it doesn't matter whether it is by itself or in that 2 heads pair, but we've got 3 out of 4 of those because we've got the heads, heads, the tail heads, and the heads, tails. Oh, sorry, 1 head. Apologies for that. Should be 2 out of 4 because we're wanting exactly 1 head. I'm thinking of the next question where we've got at least 1 head, in which case that would be your 3 out of 4, okay? Because the only case in which that doesn't happen is when we've got 2 tails. And now for this last one, we're saying, well, what's the probability of getting a heads, heads, or a tails, tails? And that's going to be the 2 out of 4 being 1/2. Now, for an experiment like rolling a dice, this is going to end up being a bit more of a lengthy process. But once you learn these probabilities, you don't have to draw a table unless you are told to, right? But if we fill out this table, it is going to take a moment. So I am just going to pause the video here and quickly fill it out myself, but feel free to fill that out on your own. So hopefully after you've filled your table out, it looks a bit like that. So in this experiment, we've got 36 possible outcomes. So if we wanted the probability of the same number being shown, we're going to look for where that occurs, right? Being like your 1, 1, your 2, 2, and so on. And in this case, that happens 6 out of the 36 times, which is a 1 in 6 chance. So when you roll 2 dice, there's actually a 1 in 6 chance that you're going to roll a double, which is a lot higher than we think it would be. Now, if we also want the sum of the 2 numbers shown being greater than 10, that doesn't include 10, right? And so we've got anything that adds up to 11 and anything that adds up to 12. So in that case, we have 3 possible outcomes, which is going to give us a 1 in 12 chance of that happening. Now, when it comes to anything that is more than the 2 steps, I highly suggest that we use a tree diagram instead. And so if I'm looking at a fair coin being flipped 3 times, well, once again, we're assuming this is heads, tails being a 50/50 chance, right? And so my tree diagram here is going to have 8 possible outcomes once I finish writing them up, okay? Now, because we're looking at a fair coin, the 8 possible outcomes are the same. They are an equal chance of happening. And the way that we get that is we multiply along our branches. So 1/2 times 1/2 times 1/2, giving me 1/8. So if we'd like to find out when just 1 heads occurs, we do have to sort of follow our tree diagram through. Sorry, let me just fix that. But we follow our tree diagram through and find out where that 1 head is. So our possible options there are things like heads, tails, and tails. or we could have a tails, heads, tails, or tails, tails, heads, right? And so there's 3 of those, meaning that it is 3 times that 1/8, being a 3 out of 8 chance. Now, if we're looking for at least 1 head being observed, well, that's the complementary of no heads being observed. So it's going to be the easiest to follow 1 branch as opposed to what ends up being 7. And so if we've got at least 1 head being observed, and we follow that tails, tails, tails branch, it ends up being 1 minus 7 in 8, 7 over 8, sorry. And so that ends up being a 1 minus 1 over 8, sorry, which ends up being a 7 in 8 chance of getting at least 1 head. Now, if we want the probability of just the second toss resulting in a head, we're not considering the first and the third, we're just looking at the second, okay? And so because it's a fair chance, it's still a 1 in 2. Now, looking for all heads or all tails, we can see that happens twice. So it's going to be 2 times 1 over 8, which is 1 over 4. Now, the last thing we can look at when it comes to things like multi-stage experiments is this idea of with or without replacement, okay? And what that does is it changes your probabilities depending on the situation. So if we have an experiment like flipping a coin, that's done without replacing the first event, right? And so your chance of flipping a coin in that second toss ends up being the same as it was in the first, because you're not, once you flip a heads, you're not then taking away that possibility. However, if we took something away and didn't replace it, so for example, pulling an M&M out of a bag and eating it, that would be without replacement, right? Because that option's gone. And so that will change your probabilities up a little bit, okay? And so experiments without replacements will actually result in different probabilities at each step of the experiment. So it's really important to figure out when you've got with or without replacement. So for this example here, we've got a barrel containing 10 balls, 7 of which are multicolored. And so these balls are randomly selected from the barrel and then they are placed back. So that tells us that we have a with replacement. Okay, now in this case, we have 3 trials in this question. We want to find out what happens or what the probability is for 2 of those to be multicolored, right? So I'm going to call these M and W. It doesn't really matter as long as you're sure what you call them in your tree diagram. But our chance of picking out a multicolored ball is 7 out of 10. And the chance of picking out a white ball is going to be 3 out of 10. And now because we're putting that ball back before we pick another one, those probabilities are actually going to stay the same. Okay, and then same for that third trial. Those probabilities are going to stay the same. Okay, and the way that we're going to find those total probabilities is to multiply along the branches. So we want to find out the probability that 2 out of the 3 are multicolored. I can see that one of those branches is going to occur if I go MMW or MWM, and then also WMM. Right, so they're the branches that I'm following. And we end up with 2 of those branches being 7 out of 10 and 1 being 3 out of 10. And so because those probabilities don't change along the way, I can actually just say 3 times and just do one of those branches. And so I have 7 over 10 times 7 over 10, which is 7 over 10 squared, times 3 over 10. So this ends up being 3 times 147 over 1,000, which ends up being 431 over 1,000. Now, when we have without replacement, it's slightly different. Okay, so for example, picking captains for a netball team, the assumption here is it's without replacement, that we can't have a captain also be a vice captain. Now, we're also going to assume in this case that we pick the captain first before picking the vice captain. And so the chance of picking a boy in this case is going to be 5 out of 9, and then a 4 out of 9 for the girls. And we're just assuming that this is all an even chance. Now, if a boy is selected to be a captain, that actually takes one of those 5 out and leaves us with 4 boys and 8 people total to be selected. And so along those second lots of branches, it's going to be 1/2, okay? Same with if we pick a girl instead, well, that leaves us with 3 girls out of the 8, okay? And so getting a boy captain and a girl vice captain is going to be 5 in 9, being that first branch, times a half, so a 5 in 18 chance. Then we have same-sex captain and vice captain, and so there are 2 possible options here. The first being 5/9 times a half for the boy, or 4/9 times 3/8 for the girl. Now, if we add those together and simplify, we're going to end up with 7/9.